to the contribution session. So basically, I will show the video. I think I need to unplug probably my headphones. In case you don't have sounds, Megan or Claudia, show me that you don't hear anything. Otherwise it would be weird. Thank you. So the first video will be a presentation work by Michael Abbott from the University of California, Berkeley in the US. And I need to share my screen as well. Oops. Sorry about that.
Hello everyone, my name is Michael Abbott from the Embodied Dexterity Group at UC Berkeley. I'm here to present our work on trade-offs and kinesthetic feedback.
Where is that? Okay, just checking. Megan, can you confirm that you're actually hearing? Okay, thanks. And you can see. Okay.
And body-powered devices for grasp assistance. Through human subject testing performed using an experimental haptic testbed, we found that the addition of kinesthetic feedback led to improved grasp force control in a virtual grasp and lift task. By applying force to the user's contralateral shoulder related to the magnitude of applied forces in a virtual environment, participants applied lower and more consistent grasp forces using an upper limb prosthesis emulator. These results show the potential for such feedback to allow users finer control over their assistive devices. Body-powered devices link the motion and force of a functional limb to that of some end effector through a passive cable system. While this cable can result in high loads applied to the user's body, it also enables the transmission of kinesthetic information back to the user regarding the state of the terminal device. This topology has been shown to exhibit superior feed-forward and feedback information rates when compared to other control mappings or user intent detection methods. This work examines the isolated role of this feedback on users' grasp force control in a study of body-powered prostheses. To do so, we designed a haptic testbed to emulate the operation of a body-powered prosthesis and allow for the systematic variation of force feedback presented to the user. In a virtual grasping environment, participants control the aperture of a gripper through motion of their shoulder, pushing and pulling on a harness and cable system, whose travel is measured as rotation of a motor shaft by an attached encoder. Energizing the coils of this motor produces a force on the user's shoulder through the same harness. A custom cable transmission converts between the rotary motion of the motor and linear motion of the control cable, along with a tension sensor to control the output force feedback. Participants raise and lower the virtual gripper with a controller comprised of a 3D printed grip, Teflon tube, and an infrared distance sensor. For human subject testing, each participant experienced 5 separate feedback levels, ordered randomly, where the feedback level determines the scaling between virtual grasp forces and physical feedback forces. Participants performed 10 grasping trials at each feedback level, for a total of 50 trials per participant. The following analysis was performed on data collected from 9 participants. Each grasping trial consisted of 3 stages. First, participants closed the grippers on the test object using the shoulder harness and grasped the object. Second, they lifted the object a minimum of 15 centimeters using the height controller and held the object for at least 5 seconds. Third, they released the object using the shoulder harness and let the object fall back to the ground level. In analyzing participant grasping behavior, we find that mean grasp force while holding the test object significantly decreased with increasing force feedback, with participants applying less than half the force at the maximum feedback condition than at the no feedback condition. Furthermore, the trend appears to be nonlinear with diminishing returns as the decrease in grasp force lessens between the higher levels of feedback. Similar trends, both in terms of shape and magnitude, are observed in analysis of peak grasp force as well as grasp force variation during the holding phase. However, participants also dropped the test object more frequently with higher levels of feedback, increasing from 4% at no feedback to 12% at maximum feedback. Taken together, these results demonstrate how the presence of force feedback can produce improved grasp force control in users. The high loads exerted at high force feedback factors typically resulted in the best grasp performance, but also left users more prone to drops, as well as potentially exposing them to fatigue over long-term use. Additionally, the diminishing returns seen in the results also indicate that lower forces could produce comparable benefits to grasp performance in assistive devices without the added weight or space of more powerful actuators or higher reduction transmissions. We look to extend these findings through several potential paths. First, we aim to observe how kinesthetic feedback interacts with weight sensation in a physical grasping environment. Second, we will study the effect of kinesthetic feedback on the cognitive load placed on the user during device operation. Finally, we will investigate the integration of cable-based haptic interfaces into novel hybrid devices, which combine passive and active components, both for prosthetic technologies and those which work in parallel with intact limbs.
All right, we will now move to the next contribution. So the next contribution is by Eisa Anwar from Queen Mary University in London.
Hi everyone, my name is Eisa and I'm a PhD student at Queen Mary University of London. This is our presentation on augmenting human balance with wearable robotics for load handling tasks. I'd like to thank my supervisors, Ilda and Stuart, for their help and support with this work. In recent years, there has been an increase in popularity with supernumerary limbs. These are extra limbs which can be attached to the human body and increase a user's physical capabilities. For example, extra arms and hands that can help people to carry more, which can increase their productivity. However, when supernumerary limbs are attached to a user, they can offset the user's center of mass and therefore affect their balance. The effect of this has not been explored. Changes in balance and center of mass could lead to safety issues, potentially in the form of accidents or unhealthy postures, which could contribute to the development of back pain over time. Various robots have been developed to assist users with balance. One example is exoskeletons, and some examples of them are shown here. Exoskeletons can provide support and balance assistance for users, for example, with spinal cord injury. They can provide stepping assistance, and they can even provide assistance in recovering from slips. Unfortunately, exoskeletons are relatively high in cost and complex to integrate with a user's body and supernumerary limbs. Another example of a balance supporting robot is wearable gyroscopes. These can make use of the gyroscopic effect to stabilize a user. Unfortunately, these have a limited stabilization force and are relatively heavy, so they would not be suitable for augmenting balance during load carrying tasks. Supernumerary limbs can be used for balance support, and there are some examples shown here. The image in the center is a project by Abashina and colleagues, and this actually inspired us. It's a wearable tail which can be used for balancing and haptic feedback. Unfortunately, balancing wasn't tested, and the system that they developed makes use of an external compressed air source, which would limit portability. Our goal is to use supernumerary limbs for material handling. We will make use of a robotic tail for balancing. We want to improve ergonomics and posture support for people using the system. And next, I'll talk about the simulation study that we conducted. We created a simulation model, and its task is to maintain upright posture. The control input is torque for the robotic tail, and the output is the anterior-posterior body sway. Human is modeled as a blue bar, and the load they're carrying is the orange box. The load is 10 kilograms, and its center of mass is 25 centimeters in front of the human center of mass. Due to gravity, when there's no stabilization, the human falls forwards, as shown in this video. These are the results with the robotic tail. And we can see from the video that the tail's action supports upright posture. Gravity compensation is also used on the tail to reduce the actuator's load. And we can see the graph on the bottom that the actuator for the tail only uses around 60 watts maximum, which is relatively small and is important to reduce any unnecessary extra weight with the system and also reduce power consumption, which could, for example, increase battery life or reduce battery size required, which could further help to decrease extra weight in the system. This final slide shows some design concepts for the system. On the left, the illustration shows two tails to limit the effective inertia to one axis. And the illustration on the right shows another idea for reducing inertia with the use of a flywheel, which also doubles as the counterbalance. Thank you.
Once again, keep your questions for, you can write your questions on the chat, on the Q&A, using the Q&A button, and then we will ask all questions at the end of this session. So the next contribution is by Nassim Benhabib, and he's from Inria, Bordeaux in France.
I am Nassim Benhabib. I am a PhD candidate from Inria, Bordeaux in France. In this video, I present our work on securing industrial operators with collaborative robots using a dedicated process simulator and its experimental validation. This work is performed in collaboration with my co-advisors Vincent Padua and David Daney. The starting point of this work is the absence of robots from many goods production sectors such as craft. This can be explained by the high level of human expertise involved in crafting and by the very flexible production process it involves. These two characteristics makes it technically and economically hard to automate such production processes, contrarily to more standardized manufacturing industries. Yet there is a strong need for assistive devices helping to preserve the craftsman's health and physical integrity while not hindering their expertise and know-how. Collaborative robotics appears as a potential candidate, and the challenge is thus to design collaborative robots for such tasks, in a quantifiable and objective manner, beyond wishful thinking. Carpentry and the wood shaping task seems to bring together the problems mentioned. A wood shaper is a machining tool used to profile wooden parts. During the shaping process, the carpenter machines a piece of wood in strong interaction with a cutting tool. However, the wood is a non-homogeneous and anisotropic material. This can lead to strong instantaneous variation of the cutting forces and destabilize the part throughout the task. This is characterized by a large variation in the workpiece velocity that the operator cannot compensate. According to our partners from the Carpentry Teaching Center, this is the origin of most tragic accidents in wood shaping and explains why many carpenters have lost phalanges. In addition, wood shaping appears to be an arduous task given the posture adopted during the operation. Given the expertise required by wood shaping and its highly dangerous nature, we chose this task as a pilot to investigate the potential of collaborative robots in the craft context. The collaborative robot may be a good solution to stabilize the wooden part during tooling. A proper approach to evaluate this hypothesis requires to analyze the various conditions of accidents and test design choices both in terms of robotic architectures and controllers. However, prototyping a direct solution in real conditions is dangerous and ethically complex. So, at first, it appears necessary to resort to a process simulator. To provide useful and meaningful information, we developed a physics-based simulator in order to reflect the wooden part dynamics as a function of its interactions with the tool and the operator. The simulator also allowed to render the varying cutting conditions due to the non-homogeneity of the wood structure. Finally, it takes account for human action and its biomechanical limitations. The simulator allowed to identify accidentogenic cases that are due to the appearance of wooden modes in the workpiece. This results in a sudden variation of the wood speed that the operator cannot compensate. Given the nature of fast velocity variation observed, a rather straightforward assistance strategy is proposed. The robotic assistance provided to the user should aim at decreasing the risk of sudden modification of the velocity while allowing to maintain direct physical interaction of the carpenter with the wood as well as his sensations. To do so, we consider an assistance architecture where a collaborative robot is attached to the wooden part and applies appropriate wrenches to it in case of disturbance. To meet the specifications, it is proposed to use the robotic system in order to damp the transient velocity change when an instability occurs. The robot-controlled torque is thus computed to compensate gravity while applying a damping wrench. The obtained results are now presented. In the proposed video, we illustrate the effect of the damping coefficient on the velocity peak when the disturbance occurs, both in simulation and experimentation. In the top left quadrant, we can see the subject performing the proposed experiment in the quadrant below. A visualization of the corresponding simulated motion of the wooden part and associated interaction forces is proposed. The evolution of the velocity of the wooden part is shown in the right side. The top right quadrant corresponds to the experimental results, while the quadrant below corresponds to the simulated ones. One can observe that the damping added by the robot provides an effective way of reducing the velocity peak and in terms of reduction of the forward motion of the hands induced by the wood disturbance. As expected, the larger the damping value, the more efficient the reduction of the peak velocity is. Very interestingly also, the simulated and experimental results are quantitatively very similar. While this does not completely validate the pertinence of the proposed assistance solution, this is still a very encouraging result regarding the quality of the proposed simulation framework. This figure summarizes the obtained results. It should be noticed that the operator manages to maintain the forward velocity of the wooden part independently from the damping coefficient value. However, this requires larger forces to be applied for high damping coefficient values. In this video, I have presented our work, which is a first step towards a design methodology for the use of collaborative robots in the craft domain. Focusing on a wood shaping pilot task, we have developed a physics simulation of this process. This simulator allows to predict the dynamic behavior of the wood part being milled as a function of the mechanical properties of the wood, but also accounting for the biomechanical capabilities of a simulated human operator. The simulator appears to provide realistic estimates of the process behaviors and could be used in preliminary design phases to perform choices in terms of robot architecture and control. However, the question of the trade-off between task safety, quality of execution, and operator comfort remains open. We believe that this issue can be addressed by adapting advanced control architectures to the expertise level of the operator. This then requires specifying and quantifying the operator's expectations in terms of sensory motor control on the task and its temporal evolution.
Now the next presentation is by Thomas Callens, and he's from Leuven in Belgium.
Hello, my name is Thomas. I'm a PhD student from the University of Leuven in Belgium, and in this short video I will introduce the controller for a quasi-passive hip exoskeleton. Before introducing the controller itself, let's first take a look at the exoskeleton at hand, which has been developed by our colleagues from the University of Brussels. In the video on the left, I'm wearing the exoskeleton. The exoskeleton provides support whenever you're lifting objects from the ground. It contains two modules, a passive back module as well as a quasi-passive hip module. The quasi-passive hip module contains a parallel spring mechanism that can be coupled or decoupled. In the figure on the right, we show the mechanism or solenoid responsible for the coupling or decoupling. As soon as a solenoid is engaged, a user will start to feel support when it's flexing forward. Apart from the solenoid, the exoskeleton also contains encoders, one located on each of the hip joints, such that we can register the hip flexion angles. The controller for this exoskeleton thus needs to decide whether to engage the support mechanism in the hips or do nothing. Our approach is to use higher order knowledge about the motions being executed, such that we can then make smart decisions on whether to engage the support mechanism or not. And we do this using decision theory. To be able to use higher order knowledge about the motions being executed, the exoskeleton needs to have access to a database of known motions. To create this database, I've recorded myself while performing different types of motions, and I've used the sensors on the exoskeletons to record myself. I've performed squat motions, asymmetric stoop left motions, and asymmetric stoop right motions. Next, using a technique called PPCA, or probabilistic principal component analysis, I've transformed these demonstrations into motion models. The black line in the figures is the mean of the demonstrations, while the gray area indicates the variance in the demonstrations. The exoskeleton then uses these motion models in the database to detect ongoing motions, as well as calculate the probability of ongoing motions. Once the exoskeleton has recognized the motion, it now needs to make a decision about whether to engage the support mechanism or not. To do this, we use decision theory. This means that we will first think of the actions that the controller can make, as well as the outcomes or situations that we can end up with. The first action that the controller can do is to engage the support mechanism. There are two possible situations that we can end up in. The first situation is the one in which the user is getting the support that he or she wants. This is a positive situation. The second outcome is the one in which the user did not want support but is getting it anyway. In this situation, the exoskeleton is hindering the user. To both of these situations, we now assign a utility or usefulness score. The green one is a positive score for a positive situation. The red one is a negative score for a negative situation. Similar reasoning has to be done for all the actions that the controller can do. In this situation, there is only one other action that our controller can do, which is doing nothing. Then for each of these actions, we can then calculate the expected utility. The expected utility starts from the utility scores for all the situations and weighs them with the probability of ending up in such a situation. These probabilities follow from the motion models that we have introduced earlier. The controller will now make the action that maximizes the expected utility, such that we always do best for our user. Resulting behavior is shown in this video. Top right corner, you can see the output of the exoskeleton. As you can see, the exoskeleton is able to recognize motions as well as estimate or provide an estimate of the probability. Apart from the probability and the detected motion, the exoskeleton is also able to provide you with an estimate of progress of the motion as well as the expected utility score. However, these last two variables are not represented here to keep the video clear. The advantage of this approach is that it's easily adaptable towards different types of sensors, as well as it's easily extensible towards different types of motions. In future work, I will try to set the utility scores of the different outcomes using a biomechanical metric, and I'll also try to evaluate the controller on subjects. Thank you for your attention.
And so finally, our last contribution today is by Atieh Merikh Nejadasl from the Vrije Universiteit Brussel.
Hello everyone, this is Atieh Merikh from VUB. I'm presenting my research journal paper about human online ergonomic optimization using family humor schemas. Working in a not suitable posture may cause many problems like work-related musculoskeletal disorders, the single largest category of work-related injuries and responsible for 30% of all workers' compensation costs. One way of improving the workers' physical health and promoting industrial productivity is to do the job in a possible ergonomic way. In some cases, it needs instruction, especially in industrial environments. Consider working there is a systematic way that can quantitate the ergonomic state of the employee, the Rebel assessment method, which assesses the worker's ergonomic situation in 6 steps and ensures that the joint degrees of neck, trunk, leg, upper arms, lower arm, wrist are calculated. Finally, by using some tables, the final Rebel score obtained. This score can interpret the ergonomic state of the worker's body posture. The lower the Rebel score means, the more ergonomic situation. This picture shows a woman is stacking some items. By some modification in neck and upper arm positioning, the more ergonomic posture obtained, and the Rebel score of each part gets shown in this difference. The main idea was first to give the customized instruction to the user by a user interface to remember the worker about its current posture and the most optimized posture that can be obtained. As stated earlier, each posture has a Rebel score, and each Rebel score consists of a Rebel array that holds the Rebel score of each joint. There is an equivalent array of twin degrees holding the angle interval based on the Rebel score. For example, for the neck, the joint angle between 20 and 16 is a Rebel score of 2. Optimization algorithm is based on getting the current posture joint degree, computing the Rebel score. In case of being greater than a threshold, we're going to reduce it. But the question is how much room reduction is possible. First, consider the person Rebel score is 5 as an example. Reduce it by 1 unit, faced with many combinations of segments Rebel score that all result in reduced Rebel score of 4. And in view of Rebel assessment method, they are ergonomically in the same degree. Choose one of these combinations and continue with that proposed to the user. one which has the minimum distance to the current posture. And feasibility of this decision will be checked. To check the feasibility, we should know that each selected robot array specifies the human joints, the brain elbow, that the human joint should move within this new constraint. This will result in new movement limitation to the user. The question that arises here is that can the person also continue to do the job under these new constraints or not? Each selected robot array. So to choose and to select and to check the feasibility of the selected decision, we go for the inverse kinematic fabric. Fabric is an forward and backward reaching inverse kinematic, and it solves for a target position, and in these new joints constraints, it can say that can the target be reached or not within these new constraints. So the fabric computationally is so fast and can solve the problem in a high computational costs, in a lowest computational cost, and is a novel heuristic method. The result is a library in Python, which can solve the optimization and propose a best ergonomic possible posture that the user can be used. And the results are also shown in the 3D Max model, and also the codes are available in the GitHub.
All right. So it seemed that I think like the last video got a little before the end, but I think it's just the video as I added. Yeah. All right. So and also for all the contributions are also the abstracts and the video will be posted on the website of the workshop. If like some of you are interested in checking more in details with the work that was described there in only 5 minutes, which is very short. So do we have questions for the presenters of these contributions? Same as before, you can use the question and answer button on the bottom of your screen. Okay, I have a quick question for actually for Thomas. So I was wondering, because you recorded motions on yourself so that you could then predict, like recognize the motion. I was wondering whether your goal is then to have like a generic model of motion that would work for many people, or whether you rather intend to go like user specifics where you have some kind of calibration and you use you learn the specificities of each user basically.
Yes, thank you for your question and for having me here. Actually, I don't really have an idea about it yet. First, what we'll try to do is just test it with subjects and see how it goes now, which is using the motion models that I have recorded. If we need any tweaking, then we can also record motions with the subjects themselves and then have a personalized approach. But it would be interesting, I think, for sure, that it would work with just a generic motion model, so that exoskeletons can be shared between workers.
Thank you. Thanks a lot for this answer. No questions. Okay, I have another question then for Atieh. I was just wondering. This is a very general question, maybe, but I was wondering. So you compute like a motion that is supposed to be better in terms of ergonomics, and you ensure that it's kinematically doable. Do you intend to check whether it feels like doable and natural for for the human, basically? Because I guess maybe you have some solutions that may be kinematically doable, but either in terms of force generation or in terms of motor control, maybe it's just very weird. So I was wondering whether it's something that you plan to address at some point.
Yes, actually, for right now, only the constant.
So we cannot clearly hear you, I think. Can you maybe just try to talk closer to the microphone, maybe?
Is it okay?
Yes.
So right now, just only the kinematically being feasible is being checked, and but the dynamics and the force and torque maybe it should be checked in the next step. But right now, I will do it. Thanks for your question.
Thank you. Thank you very much. Still no question? Okay, I have one last one, and then after, if no one still has a question, we can move on. So it's for Eisa, actually, about the robotics, the robotics tail to stabilize or to help balance. I was just unsure how you plan to control the tail, basically, whether it's like some kind of somehow passive reactions, or whether you have some anticipation of motion so that you can control it, maybe in a more efficient way.
Hi, thank you for having me. Can you hear me?
Yes.
So we're considering a few ideas. Firstly, we're actually looking at having the user stand on a force plate, and then we can measure roughly where their center of mass is to determine where their balance is. But we're also looking at some wearable gyroscopes as well to try and understand the basic orientation of their body and how they might need to be supported with balance. And we're considering some newer ideas as well and some different ways that we can do this.
I have a follow-up question. As you start to move, or assuming once you move from simulation to putting the system on a real human, any thoughts or considerations of how the human may adapt or have to learn how to use the device?
At the moment, with the simulation we've done, it was just like a really basic cuboid. So yeah, there wasn't much in terms of that there. We're considering comfortable ways that we can mount the robot to the human. And then we wanted to experiment with automatic controls to see, for example, if a user is carrying something, how the tail could respond, and then how the human body would respond to them as well, perhaps with use of EMG sensors on the human's body to understand how they will respond to the robot, and then potentially tweak the controls from there as well. Because it's possible the robot could provide, for example, a slightly unhelpful behavior, and the human just uses their, for example, posture muscles to stabilize them against it. So we want to make sure we're actually helping.
Yeah, excellent, thanks.
Thanks.
Okay, we have one question for the audience, so let's take it. So it's for Thomas, actually. Can the pPCA models that you extracted from the motion be used across, well, okay, no, I think sorry, I'm reading the question, but I think it's more or less the same. From the question, be used across user, or is it user specific? So yeah, I think it was already answered, sorry about that. All right. So if we have no other questions, so we are quite, let's say, very late. We were supposed to have a break. I think we can still maybe shorten the break, but like, let's say, take 5 minutes so that we can grab coffee or whatever. And then we will be back in in 5 minutes. So at 3:20, and we will move on to the next talk to try to catch up a little bit with the delay that we have. So see you all in 5 minutes.